Good morning, everyone. It's a pleasure to be here on the last day of GeeCON conference. A pleasure to see so many people excited to hear more about quantum computing. And my name is Vorhemus. I work as a consultant for Microsoft. And prior to this talk, last week actually, I gave this presentation to a colleague of mine. And he was sitting there patiently listening to me. And in the end, he said, mate, are you crazy? Everything is full of formulas here. People will get very unhappy when they see that. And I said to him, look at the title, right? This is the goal of the talk. But actually, he convinced me that I should actually remove the math a bit, and I threw away 80% of all the formulas. And I still have them with me. So if you're interested in all the math behind, come to me after the talk, and I'm happy to share it with you. But other than that, I tried to remove math as much as possible and still make it understandable. Nevertheless, I thought about another introduction to make people unhappy, and what is a better way to make people unhappy than a test? And this is where we started now. We make a little test with you, and please take all your mobile devices out, so your iPhones, your Androids, your Windows mobile devices, and please go to the following site. It's called Slido, slido.com. It looks like this, slido.com. Oh, sorry, you don't see it right now. Let's just skip it here. All right, that's the one. So on the left, you see slido.com. And it's okay. And when you open your device and you go to Slido, you have to enter a code. And the code is also right here. It's D561. And when you enter this code, you will get forwarded to a survey. And the survey is a question which is called, how much faster can a quantum sorting algorithm sort a list of integers, or list of numbers, faster than a classical computer on average? Is it A, it takes the same time, B, 2 times faster, C, 10 times faster, or D, it takes n to the power of n times faster, where n is the number of qubits? So the votes are coming in. Very excited to see this. I'm pretty interested what the result will be. Just let's give it a few minutes to see what people think, what is the right answer. Just use your intuition, right? This is not a real test. Just use your intuition what you will think is the right answer. Okay, we have interesting results coming in with D and A. D is leading, A is in the second place. A is getting more votes. Interesting. Let's see. No one takes B or C. All right, it looks like someone is influencing the e-vote, right? D is still leading, A is getting closer. 51 votes, okay, that's very interesting. We have two leaders here, D and A. Very interesting. Okay, 64 votes, A is shrinking again, and D is actually still leading. And B is chosen, and C was chosen as well. Very nice. 1 people chose B and C, so interesting. Okay, maybe I should give you the right answer. And the right answer is actually A. It takes the same time. So a quantum sorting algorithm isn't faster than a classical algorithm. Oh yeah, now A is getting higher, of course. Let's go. Let's go back to the presentation then. All right. So A was the right answer. So it isn't faster than a quantum sorting algorithm, which is may a surprise for some of you, because of course you've all heard that quantum algorithms, quantum computers are so much faster and can outperform classical computers in any way. And it's interesting to see that this is not the case, right? At least not in all examples. And I've done this survey, this presentation for another groups as well, and in the past, and the results are always the same. So always people thought that they were much faster than classical computers. And I asked myself the question, why is that the case? Why do people think that quantum algorithms must be faster? And in the last weeks, I collected some news articles about quantum computers, and I brought some of them with me. Let's just start and dive in what people have written about quantum computers. So the very first article here I found was 20 entangled qubits bring quantum computer closer. It was on 16th of April, so pretty new. looks good, right? No one understands what's going on here, but 20 entangled qubits, that sounds good. This brings this quantum computer closer. Then I found this one. It says, quantum supremacy will soon be ours, says Google as it reveals 72 qubit quantum chip. Okay, now we have 72 qubits. This brings us closer to quantum supremacy, whatever this is, but 72 qubits, and then we are there. All right, next article. We have D-Wave, and they put a lot of money into their quantum computer, and they have already 2,000 qubits. Okay, we have 3 articles, 3 numbers. Let's take a look at the next one. IBM edges closer to quantum supremacy with a 50-qubit processor. Okay, and now we have the last one. Here's why 100 qubits quantum computers will change everything. All right, we have 5 articles. We have 5 different numbers. No one knows what's going on. We have qubits, entangled, supremacy, whatever. And what actually is happening here, right? How many qubits will change now everything? What can we do with the qubits? What is entanglement? What's going on? And it looks like actually no one has a clue. No one knows what's going on here, right? And then I asked myself the question, maybe when quantum computing is so hard and so not understandable, why are we actually dealing with it? Why don't we just continue to build classical computers and make it faster? And this is actually also the first question I want to ask you. Why do we need quantum computers, actually? Why do we need it? And to answer this question, I brought a graph with me, a chart, and I'm pretty sure you have all heard about it. It's a chart that, or a law that Gordon Moore has formulated in 1965. And the basic meaning behind this law is that our transistors on a chip, the number of transistors we can put on a chip double roughly every 2 years, right? And this law was pretty accurate till now. So this was always, it was slightly modified in the 1970s, but the basic principle behind was pretty accurate. But now you see here on the right page, this year 2020, this is not arbitrarily chosen, this is on purpose. And you also see that this chart here on the top is actually hitting the roof, right? So it's actually, we're getting to some borders here, and this is a very interesting observation we have. We're putting already so many transistors on a chip, so the transistors getting tinier and tinier, that we're actually coming from a classical world to a quantum mechanical world. Because in this tiny world, new spooky effects are happening. And I want to show a picture to you of a very interesting transistor. This is actually one of the smallest transistors that was ever built. It is just, you see it down here, it's made of carbon nanotubes, and it's 1 to 2 nanometers long. And this transistor is actually acting as a gate, right? So it can pass when it's open, the electrons can just flow through, and when it's closed, these particles are just blocked. So how a transistor works, a gate works. But now in this tiny little world, some new interesting effects are happening. You have this transistor and you have a particle, and this particle tries to go through, but sometimes an effect called quantum tunneling is happening. Quantum tunneling, just to describe it in a very, very naive computer science way, not in a physicist way, is that particles can suddenly disappear and appear on another side without any barrier that is blocking it. Which means I have my gate, my transistor, it is closed, the particle is coming, it's just vanishing here, disappearing here again, and just flowing back then. Which makes this transistor, this gate, pretty useless, because these particles can just flow through, no matter if this transistor is open or closed, right? And this actually leads to big problems, because we can't actually build smaller transistors that can still control these particles. And this is the world where quantum mechanics comes in. So this classical world, we leave the world of classical physics and go to our quantum mechanical world, and we see these effects, right? So we can't really remove these effects. They're still there. This is how nature works. And so some smart people, smart researchers have asked themselves the question, okay, we have these effects, we have these quantum effects, they're there, we can measure it, but maybe we can use these unwanted side effects and make something beneficial out of it. Maybe we can use these quantum effects to make computers out of that. And this is actually the plan behind quantum computers. So we use the effects of quantum worlds and try to make calculations with it. And I want to bring an example to you. Now, I've already burned you with the quantum sorting algorithm. Here's another chance. The question is, let's see, we have a long list of integers, right? And we want to search a specific number in this array, in this array. And this is not indexed and it's unordered. And the question is, how long does it take to search this element in the list. Now, to visualize it, we have just a list, an array, and this array has a length of n, so 1 to n, and we are looking for a specific number, so for example 1, 2, 3. How long does it take to search through this list and find the number 1, 2, 3? As you all know, on a classic computer, and as you may know from theory, there's a specific explanation to describe this. This is big O notation, and it takes n time steps, time complexity is n, which means in the worst case, you have to look through all elements in the list because the element you're looking for could be in the very last place, which means you have to look through all of them to find the element you want, right? On average, it's n half because it will be somewhere in the middle, but in the worst case, it's in the very end, and you have to look and you have to go through all of them. Okay, this is a classical computer. Let's take the same question and reformulate it a bit. How long does it take to search an element in an unordered list with a quantum computer? And now you may think, oh, it's again O of n, but the answer is no, not this time. The answer is it's O square root of n. Let us think for a moment. It means on a quantum computer, we can search a list of elements and we don't have to look through all elements. We can have a quadratic speed up here on quantum computers when we look for a certain element in a list. Isn't that crazy? Isn't it magical? You don't have to look at all elements to find the element you want. How is this actually working? And in this talk, I want to bring you an algorithm closer to you, which is actually doing that. It's called Grover's algorithm. And Grover's algorithm is right here. This is how Grover's algorithm works. Pretty simple, right? Okay, then we can go to the next one. No, of course not. This is Grover's algorithm, and when you see this for the first time, you may think, what's going on here? You have these strange notations here, strange gates we've never seen before. So what is actually going on behind this Grover's algorithm? And I want to, when you walk out today after this talk, I want you to bring or gave you kind of a tool belt. So when you see something like this in the future on papers, on books, you have a better understanding of what's going on behind these quantum gates, quantum circuits, quantum processors, and just know that when you see this, you've seen this before in my talk, and you already know what's going on. Okay, so we talk about things like, here on the very left, we have an element called the Qubit, which is basically the basic element of quantum computer. We have things like these gates, which are turning qubits into superposition, very exciting. And we have also things like this, which are basically quantum gates. And we will talk about all of them and give a short description of what these elements are doing in quantum computers. All right, then let's start with the very basic one. A qubit. And the question, of course, arises, what is a qubit and what can we do with a qubit? And I'm pretty sure you're all familiar with, we are all developers, all computer scientists, at least most of us. We all know what a bit is, right? A bit is just a state, just an element that have two states, 0 and 1, or true and false. And a qubit is very much the same concept. It also has two elements, two states, 1 and 0, or true and false. But it also has some new effects, some new elements called quantum effects, which are affecting this qubit. So a qubit can be actually anything when it has quantum mechanical properties on it. And there are, of course, some restrictions. We also have to be able to control this qubit, of course. We have to, for example, control it in a way that it can flip from 1 to 2, from 1 to 0, from 0 to 1. So there are limitations, but in the end, everything could be a qubit. And I brought 3 examples with me. I have listed them here. The very first one, the left one, is an electron spin. The second one is a photon polarization, and the last one is energy level. And I want to start with the electron spin. And by the way, when you see some notations like these, or this electron, electrons don't look like this, right? They don't look like a ball with fancy arrows. This is just always a visual representation, because in this quantum mechanical world, there is no real good visual representation we can give. This is just to make it more convenient to look at and to have an understanding of what's going on. But basically, electrons can have a spin, and a spin is a quantum mechanical property. And it's very hard to describe what a spin actually is. Even physicists don't know it in the end. It's just producing a tiny magnetic field, but it's not like rotating or something. This was a very bad naming convention. It's just here, every electron can have a spin, and it's producing a field, a magnetic field, but it's not really a rotation of the element. And the interesting thing about electrons is, or electron spin, that it can rotate in different directions. So the spin can be spin up or spin down, just to visualize it. The photon polarization is can also be used as a qubit because it has, since photons are polarized, or photons that are coming out of the sun, for example, are polarized, which means they have a they're aligned in two different directions. So there's a vertical alignment and a horizontal alignment. So two states which can be used as a qubit because we have two states, 0 and 1, right? And the last one, energy level, I won't talk about this too much. It just means that particles can have an energy state, it can be excited or non-excited, and these two states can also be used as a qubit. So when we talk about electron spin, how can we actually use this? How does it look like? Now, suppose or imagine you have an electron in a kind of a trap, in a kind of a field, and you can control it. And this electron, the spin is pointing down right now, right? And this pointing down, this is equivalent to the qubit position 1 and 0. So when it's pointing down, we describe this as being in a state 1, and if it's pointing up, we describe this as being a state 0. So this strange notation you see here, so these brackets here, these are basically just Dirac notations. And don't be afraid of these notations. They just mean we just use them to distinguish a classical bit from a qubit. So this is just a qubit, nothing special coming here, just a state 0 or 1. Now we can control this qubit and apply some waves. So this qubit is flipping from the 1 state to the 0 state. This is actually really easy for a physicist. You can do this. You can just flip this bit from 0 to 1, from 1 to 0, very easily. But now the first magical part is coming in the quantum world. You can't just only flip this qubit from 0 to 1 or from 1 to 0. You can also bring it in kind of a middle state. You can bring it in a state between 0 and 1. So this particle is in two states at once. So when you hear this for the first time, you may think this is... what is this, right? What means 0 and 1? It must be in one state. But actually, measurements showed and physicists showed that it can really be in two states at the same time. And this is something you can't really understand. At least I can't understand it. And just accept it as it is. This is how quantum mechanical worlds work. And you see, I wrote this strange notation where I put the 0 and the 1, I'm overlapping it. And this was just my interpretation or my notation to write the states 0 and 1 at the same time. Okay, but there's another interesting thing going on here. Because this superposition, this is how it's called, the superposition, a position of two states, this is only valid, or this only takes place, or this is only like in superposition when we don't influence it. When we influence this particle by just throwing photons on it or any waves on it, or even heat can influence that, it automatically collapses to one of the states. So when we measure it, and measuring always means influencing the particle, and I'm just visualizing this by this glass, this particle will automatically, immediately collapse to one state. So in this example, it was collapsing to the state 0. Could have also been possible that it's collapsing to the state 0, it's here, and it's 1. It could be also be possible that it's collapsing to 0. And this means we can't really never observe superposition. We just know we can bring particles to superposition, and when we measure it, it will collapse to 0 or 1. Okay. Now, since we really can't calculate with these representations, these Dirac notations, how they are called, mathematicians have found a better way to make this more convenient. And what mathematicians always do when they don't know what to do, they bring it in some form they can use and they can calculate with. And this is actually what is done here right now as well. So we have this qubit 0 and 1, and this qubit can be represented as a vector, as a classical vector. And since qubits can be in two states at once, so 0 and 1, we have to use vectors with a length of 2, right? And this left qubit here with state 0, it has a vector representation where the first element of the vector is a 1, and the second element is a 0. Vice versa, when you have a qubit with state 1, the first element is a 0 and the second element is a 1. This is just a naming convention. This is just how computer scientists have chosen that this is how a qubit with 0 should be represented, and this is how a qubit with a 1 should be represented. Now, we also have this strange superposition, and I chose this notation to write this. But it turns out mathematicians have found a better way or a better notation to describe this. Superposition can also be described like this. So don't be afraid. It looks strange. It looks when you see this Greek characters, it's always a bit complicated. It looks complicated, but it's actually very simple. So here we have our qubit. This is psi, just an arbitrary Greek character. And this superposition, this qubit in superposition, is composed or is created from this state here. And this alpha, this is a complex number, but doesn't really care. We don't really care what it is. In the end, it's just it can be represented as a probability that this qubit can collapse to 0 or 1. So we have a certain probability that it collapses to 0. We have a certain probability that it collapses to 1. This can be also described as this. So since A and B, alpha and beta, are complex numbers, it's not really a probability, but you can just think of it like a probability, right? So alpha kind of represents how the probability that this qubit collapses to 0, and beta describes or is the probability that this qubit collapses to 1. Okay, let's take a bit more math, not much more, but just to give you an understanding. When you see this somewhere in papers or books, you know where this is coming from. Let's suppose we give our alpha the number 1 over square root of 2, and beta also 1 over square root of 2. Now, if you square these two numbers, you will get the result of 1. Because when you square 1 over square root of 2, this is 0.5, which means the probability 0.5 that this qubit collapses to the state 0. And beta in this case would be 0.5 as well. Probability 50% that this collapses to 1. And of course, the probabilities must sum up to 1 in the end, right? So every time you see this 1 over square root of 2, don't be afraid, this is where it's coming from. There is actually also another naming convention or another way to write superposition. It looks like this. And when you see it in papers or books, again, don't be afraid. This is just a way to write superposition as well. You have this 1 over square root of 2, and just you multiply it with this 0 or 1 qubit, and this also just represents superposition. It can be in both states or is in both states at the same time and collapses to one of the states when it's measured. Okay? Great. Then let's take a look at how the vector representation looks when we have 1 qubit. We already know that. So 1 qubit with state 0 can be represented as a vector with the first element 1, and the second element is 0. Now, what happens when we have 2 qubits? It looks like this. So we have 2 qubits. They are still in this bracket notations, 0, 0, and it can be represented by a vector with the length of 4. And just the first element is a 1, and all the other elements are 0. And maybe you're interested to see how this is calculated. It's actually not so complicated. So maybe I'm just trying to do this right now. Suppose we have 1 qubit in the state 1. And we have a second qubit in the state 0, and the second qubit also in the state 0. And we now want to bring these 2 qubits together and get the vector of this qubit. So we have the qubit in state 0, which is a vector representation with 1, 0. And then we use an operator called the tensor product. Tensor product looks like this. It's a circle with an x inside. And we use the second qubit, which is also in state 0. And this is actually how you calculate it right now. So you take the second vector, which is this one, write it down here, and you duplicate it. You write it twice. And then you take this vector here, and you split it up. You split it up in a way that you put the first element up here, and the second element down here. And then you just multiply every element in this vector. So you multiply 1 by 1 is 1, 1 multiplied by 0 is 0, 0 multiplied by 1 is 0, and 0 multiplied by 0 is 0. And the result you have here, this is just our representation of 2 qubits. Okay? So when you see this tensor product, the circle with an x inside, this is how you combine multiple qubits to a vector. All right, and when you closer look at this representation and all these qubits which are combined together, you may see a certain pattern right here, right? So we have 1 qubit, which can be represented by a vector of length 2. We have 2 qubits, which can be represented by a vector of length 4. And when you have, let's say, 300 qubits, the equivalent of 300 qubits would be classical bit 10 to the power of 90. So we have a exponential number of qubits we can use to represent a much higher number of bits. So 300 qubits would be equivalent to 10 to the power of 90 bits. And this is actually also where the power of quantum computers is coming from. You just need slightly less qubits than bits to make the same calculations. And this is also the reason why a lot of people think that quantum computers must be faster, because they just see these calculations and see, okay, we have 2 qubits which are equivalent to 4 classical bits, and 300 qubits are equivalent to 10 to the power of 90 bits. It must be faster, so let's write an article about why 100 qubits change everything, because it must be faster, right? And the sad story is that this is not the whole story. Qubits are nice. It's a good a good way to start, but qubits alone are not everything to make quantum computers faster. And to understand why, we have to take a look at another interesting principle in quantum computing, which is called entanglement. And entanglement is, again, a very spooky and very interesting thing that happens in the quantum world and doesn't happen in the classical world. Let me briefly visualize how this works. So for entanglement, you need 2 qubits or 2 electrons, and you bring them close together. And what you do is, with the first qubit, you bring it to superposition, which is represented by this nice rotation about 90 degrees. What you do then, you influence the second qubit with a certain wave, which leads to a kind of a flip of the second qubit. But it doesn't really completely flip. It's also in kind of a superposition. And when you do it like this, these two particles are now entangled. And entangled means that these 2 particles now have the same state. Doesn't matter how far you divide them. So you can get one particle to, the moon and one on the Earth. And when you measure one, you immediately know the state of the other. But it's not pre-checked, so this is still in superposition. Both are in superposition. But when you measure it, both have the same value. And this is kind of strange, right? Because they somehow exchange information, but they don't really exchange information. And this was what Einstein called spooky action at a distance. It has no real explanation for why this is happening. And quantum mechanics can explain this. This is just entanglement, right? This is how it works. This is how our quantum world works. And when you finally want to make use of all these things, of qubits, of superposition, of entanglement, you need some kind of calculations, right? And to bring this closer to you, let's start with classical logic gates. And I'm sure you are all familiar with that. We have classic gates like the AND gate, we have the OR gate, we have the NOT gate. And of course, you all know how this works, right? This is how classical computers work. And you can combine all these gates and make calculations with it, right? So this is how classical gates work. And in contrast to that, we also have quantum gates in quantum computers. And they are actually not the same as classical gates. They also act like gates, but they do different operations, different calculations on these qubits. And the interesting thing here is that the quantum gates, they can use 1 to n qubits to make calculations, and they use things like superposition and entanglement to do these calculations. And I brought 3 with me today. The first one is the Hadamard gate, the second one is the Pauli X gate, and the third one is the CNOT gate. And we go over all 3 of them to just give you an idea of what these gates are doing when they're applied to qubits. So let's start with the first one. Let's start with the Hadamard gate. When you want to visually represent the Hadamard gate, we can do it like this. So you have a qubit, and you have this horizontal line, and this horizontal line is actually describing a circuit, or you can just think of it like a timeline. Every operation that is done on the left is prior to everything that is done on the right? And you can put gates on this timeline. And for example, I can put my Hadamard gate on this timeline. And the Hadamard gate is represented by this nice rectangle with an H inside. And this Hadamard gate is actually bringing our qubit into superposition. So in this example, we have a qubit of 1. We send it through the Hadamard gate, we bring it to superposition, which just leads to this kind of equation, you already know that, which means it's in the state 0 and 1 at the same time. And now, in the end, we can measure our qubit. So we need another gate. This is called the measurement gate. And when we measure it, this qubit will collapse to 1 state, 0 or 1. We can't decide it in advance. This is just random, or at least we haven't found what is actually causing that it's collapsing to 0, 1. It's in the end random, right? So this is how a very simple quantum circuit looks like. You have the qubit, you have the Hadamard gate, you apply the gate, and in the end you measure the result. Okay? Now, I also have the math with me. I'm not sure if I should show it to you or if you don't wanna, if you wanna skip over the math, but let's do it. Let's just look at the math to make you unhappy. That's actually the idea. So this is how the math behind Hadamard gate looks like. It looks complicated first, but let's go over it step by step, and it's actually very simple. So we start right here at the left, right? So at the beginning, at the left entrance here. And we have our Hadamard gate represented by the H, and we have the qubit with state 0. What we do now is we apply the Hadamard gate to the qubit. The Hadamard gate is actually a matrix represented by this part here, right? It's just a matrix. And our qubit, you already know that, is represented by a vector, right? And all these quantum operators are in the end just matrix multiplications. This is all we do. And we do this by just multiplying our 1 over square root of 2 with our matrix here, which leads to this result. And then we just multiply this matrix with this vector, and the result is this one. And this already looks familiar, right? This very right vector, this 1 over square root of 2, these are just can be represented as a probability that the qubit is collapsing to state 0 or to state 1. Okay? Now, when we take a look at Hadamard gate applied to a qubit with a state 1, it's actually almost the same. So you also have the Hadamard gate, you apply it to the vector. The vector looks different, of course, because it's now in a qubit in state 1. And you apply this, and the only difference you see here is this sign. The sign is a minus instead of in plus. And the reason for this is that all the quantum operations we do have to be reversible. So when we now apply, or when we now multiply this vector here, this vector, again with our matrix, the result must be this vector again. Same case here. When we multiply this one with this Hadamard gate here, the result must be this vector again. Okay? This is true for every quantum operation. So every quantum operation, no matter what, must be reversible. When you have the end state and you just apply the state you just applied before, you must get the beginning, the first vector again. Okay, not so hard, right? Let's go to the next one, the Pauli X gate. Now here's how it looks on the circuit. We have our qubit again. In this case, it's 1. Then we apply our quantum gate, which is the Pauli X gate represented by this rectangle with an X inside. And then we have our measurement gate. And what this Pauli X gate is doing, it's just flipping the bit. So when the qubit was 1 first, it's getting 0. When it was 0 first, it's getting 1. So in the end, we would measure 0 because the qubit was 1 first, right? And when we represent this mathematically again, it's actually much easier than the Hadamard gate. We just apply the NOT gate. It just looks like an identity matrix, but just like mirrored, right? So we have this 0, 1, 0, 1. We multiply this by the vector, and the result is just the opposite, okay? So in this case, we have this vector, which represents the qubit 0, the qubit 0. And the result will be this vector, which represents the qubit with state, with state 1. Okay? Same when we apply the Pauli X gate to our qubit with 1, then we get, as a result, we get a qubit of 0, right? So nothing special here. Okay, the last gate is an interesting one. It's called the CNOT gate. And this time we're using 2 qubits. And the CNOT gate is flipping a qubit when the control qubit is 1, otherwise it's doing nothing. So in this example, I have the control qubit on top, and we have the qubit we want to control on the bottom. And the control qubit is 1 in this case, right? And if the control qubit is 1, the bottom qubit is flipping, so just turning around from 0 to 1, or from 1 to 0. And this is exactly what's happening here, right? So we have our control qubit is 1, and this is why our bottom qubit is just flipping from 0 to 1. That's it. That's all what a CNOT gate is doing. We can apply this CNOT gate not only to 2 qubits, but n number of qubits. We can also have 3 control qubits, which are controlling just 1 qubit, okay? And this is how it looks like on when you apply matrix multiplication again. So we have just this CNOT matrix, which is here, and it looks very it looks kind of like the identity matrix. The only difference is that these two numbers are flipped here. And this is actually leading to the flip of the gate, which is controlled. Okay, and I can send you the slides afterwards, so maybe you will see the slides anyway. These are just the representations of these CNOT gates, and when you can, as you see, these are controlling the qubits in a way. For example, let's just go through it for us for a time. So this is the first one here. This is our control qubit, and this is the qubit that should be controlled. And you see this one is 0 here, and that's why nothing happens here. Same here. The first qubit is 0, and this is why nothing happens here. But when the control qubit is 1, you see that the second qubit is flipped. So from 0 to 1, right? Same here. The first qubit is the control bit, and the second qubit is the one we control. And since this is 1, this is getting flipped from 1 to 0. Okay? And our interesting thing is that we can also combine these gates. Now we can have Hadamard gates, we can have Paul X gate, we can have CNOT gate, and just put them all together on our quantum circuit and can make calculations on it right now. So for example, in this case, this example uses Hadamard gate and a CNOT gate, and this is actually this is the formula for creating entanglement on quantum computers. You have a Hadamard gate, you have a CNOT gate, and in the end, both qubits will be entangled. And we will take a look at this in a few minutes in the demo. But first, before we do this, let me just briefly come back to our algorithm I have shown you before, Grover's algorithm. Grover's algorithm is a quantum algorithm that runs on universal quantum computers and can actually search for elements in a list with time complexity square root of n instead of n on a classical computer. And let's take an example to make it easier, right? Let's suppose we have 3 qubits. And with 3 qubits, we can represent a database or a list of data with 8 numbers, because 2 to the power of 3 is 8. And let's suppose we want to check if the number 5 is in the database. And when we want to describe 5, the decimal number 5 in binary form, it's just 101. Okay? Now we have 3 qubits. These are represented here on top. So the first three qubits are our database. And then we apply some operations, and then hopefully we will find out if 5 is in the database or not. And to do this, there is an element called an oracle used, which can be found here. It's this big rectangle with an O, and here all the magic happens, and it's hidden, of course, right? But we can take a look inside what's going on here. And now this is very interesting, because what we do here is we apply Hadamard gates to all our qubits, and these Hadamard gates, these are all bringing our qubits into superposition. We already know that, right? So all these qubits are now between the states 0 and 1, and are then applied to the next gate. And the next gate is a Pauli X gate here in the middle. And this means this only flips the second of our 3 qubits, okay? Which means when a 0 is coming in, this qubit is turning to 1. And if a 1 is coming in, this is turning to 0. Now, when we take a look at our binary form of 5 again, okay? This is 1, 0, 1. And now suppose from all our from our superposition states, everything is coming in there. Everything that's in our database, the superposition is coming in there. So all the numbers at once. Only the number 5, represented by 101, will flow through and will just flip this gate below here. Why is this happening? Let's take an example. Let's suppose the number 1 is coming in, or the number 0. If the number 0 is coming in, we have all the 3 qubits will be 0, right? And when you take a look at the first qubit, when it's 0, the CNOT gate is not flipping, because the CNOT gate, which is seen here. So this is a CNOT gate. This only flips, so this bit here only flips if all these 3 qubits are 1. So if 0 comes in here, this is not flipping, right? So if any of these elements are 0, nothing happens. This is only flipping if this is 1, this is 1, and this is 1, and this is only turning 1 if the entrance here is 0, because it's flipping here, okay? So this means if this is 1, if this is 0, if this is 1, this bit is flipping. And when you look closely, this 1, 0, 1, this is a number 5. So if the number 5 is coming into our CNOT gate, the very last qubit is flipping and just giving us a hint or a sign that the number 5 is present in the database. Now, when you hear it for the first time, this looks very complicated and strange. Let me give you a more visual representation of what's going on behind here. So our particles can be represented as waves. And waves have a very interesting property. Waves can interfere with each other. And wave interference means when the phase of the wave is the same, the amplitudes are just getting constructively interfered, so they're getting higher in the end, right? And if the phase is different, you see it on the right side here, this gets distracted. So when the wave is different, the phase is different, the amplitudes are getting vanished to 0. And exactly this is happening on our Grover's algorithm. So these are waves, and let me just represent it here with 3 waves. And when you look closely, you will see that these waves are shifted. So the phase is not the same on every wave. Okay? And when we apply quantum gates, quantum operators, this is actually what we're doing. We're just shifting, we're just manipulating the waves in a way that when we just overlap all of them, we get some new pattern here. And hopefully when we measure this pattern, the result will be something like this. And this means we have on the x-axis, we have all our numbers, 8 numbers, that's what we had. And we have the probability up here, right? The probability to find a certain number. And we see that this pattern we get from our wave interference is looks kind of the probability function we have here on the right. So it means there is a certain probability that 5 was in the database. Now, this looks maybe strange because on a classical computer we are used to get a very precise result when you do a calculation. On a quantum computer you don't get this. You get just more like a probability that the result is right or there or not there, but you don't get a precise outcome. The good thing is when you repeat this algorithm, the probability is getting higher and higher that you find the right answer in the database. So you can just repeat the algorithm and you get more closer to the probability that it's really in there or not. Okay. Now that we have seen so much theory, let me just briefly go for the last 6 minutes over a new interesting algorithm or a new interesting language that Microsoft has developed recently, and this is called Q#. Q# is a new programming language from Microsoft Research that was specifically designed for quantum computers. And even though we don't have quantum computers yet, at least we don't have really powerful quantum computers yet, we already have languages to write quantum computers. And this is what I want to show you in the next minutes. So if you take a look at this one, maybe you're familiar with that, maybe you've seen this before. Do you know what this is? Which language? Yes, exactly. This is assembly language. Yeah. And assembly language was used in the early days of computing. And when you take a look at Q#, you may find some similarities to assembly language, because what we do in Q# is we are actually manipulating the qubits directly on the hardware. So we're actually manipulating the qubits directly and not using a high-level programming language. It's actually it's a mix between an assembly and a high-level programming language. Let me just show this to you to get a better understanding of what Q# is doing. Okay, so I've opened Visual Studio. Oh, by the way, when you want to use Q# yourself, you can just simply go to any search engine you want. Of course, I always use Bing, but you can also use others. And you can just type in Visual Studio Q#, and there is a download instruction to download Visual Studio. It's free. Everything is free and no licensing. And also the Q# development kit. And the good thing is, or the good news, you can use Visual Studio with Q# on all your platforms. So it's not only Windows, it's also you're running on Mac OS and on Linux. And when you open Visual Studio, you will have the possibility to add new projects here on the file, new projects, and then you can make a new Q# project. I've already done this before and have created a very simple Q# project. So let me briefly show you how this works and how this looks like. Now, when we develop quantum algorithms or quantum computers, we don't only write code for quantum computers. We also write classical code we are used to, right? And You see here, hopefully it's large enough. This is my project, and we have at least 2 files in here. We have this bell QS, and we have this driver C# file. And essentially, in Q#, you always use a classical code, like in this example, C#, and this code is actually controlling the quantum operations. Okay. So let's see what's happening here. We start with our C# file. It's very similar to Java when you haven't used it before. It also has this main method here where everything starts. Let me just make this a bit bigger so you can see it better. Is this okay? Okay. So we start with the main method here. And then in the first step, we create a new quantum simulator, a new object in the quantum simulator. Okay. And this simulator is then used to perform our quantum operations directly on my PC. So this is a simulator. I sadly don't have a quantum computer with me, but this is running on my classical computer as in the simulator. What we do next is we initialize new variables, and this is a data type called result. And the result can either be 0 or 1, right? This is the states we have in quantum computing. And with these results, we just run a for loop, and we use first we use our 0 states to run this for loop, and then we use our 1 state to run this for loop. And now a very interesting thing happens here. In this line, line 80, we run our quantum operation. So I've named my quantum operation bell test, and bell test is just opened with my quantum simulator, an arbitrarily chosen number. It's 1,000 in this case, which just means run the quantum operation 1,000 times just to make the result more precise. And we go now to our quantum program, which looks like this. And this is Q#, okay? So this is the new quantum language that Microsoft has developed. And all the operations here are named operations. So everything you do on a quantum computer has an operation. And this is actually, you can think of it like functions or methods. And every operation also has an operation body where the calculations actually take place. And now, a few things happen here. Now, first of all, we have some variables. So in Q# you also have variables, but all the variables are by default constants. When you want to have a real variable that is variable mutable, you have to define it by this mutable keyword here. Okay. And what we do here is in line 26, we actually create a qubit. So with this statement, qubit and then this index 1, we just create a new qubit. Okay. And then we loop over, then we use this loop to go over a certain state for 1,000 times, okay? What we do first here is we set our qubit to a certain state. So the set operation is defined here. This is not predefined. This is just using a qubit. It takes 1 qubit as an input parameter, and it takes the desired result as an input parameter as well. So desired result can be 0 or 1, okay? And what we do it then is we measure our qubit. So here you see the measurement gate the first time. So this M is a predefined function, which means measure this qubit. Okay? So we measure this qubit, which is passed over to the function. And we just check if the measurement, so if the qubit has the same state like the desired state. So if we want our qubit to be in state 1, and we measure the qubit and it's not in state 1, we just flip it. And the flip is happening right here. So we have our X gate. And we all know that already, right? Our X gate is just flipping the result, and we don't actually have to return some element because our qubits are already manipulated, so we don't have to return any value. And this means we can make sure that our qubit now has the value we want, 0 or 1. What we do next is we measure our qubit we have just set, and then we just check if the result, so the measurement is 1. And if it's 1, we just add a number here and just count how many 1s we see. We do the same with 0 as well. Okay? And then when we are done, we just set our qubit to 0 again, just to make sure it's set to 0 again, and we return the result. So we return how many times have we seen a qubit with 0 and how many times have we returned a qubit with 1. And then here we just write our program and just let this program write down on the console how many times you've seen a 0 and 1. And when I run this now on my computer, let's check if this is working. Now I'm just running a real quantum program on my computer. A simulator, of course, but still it's running. And you see here are the results coming in, and hopefully it's not too small. But what you see here is that we have measured 0 1,000 times when it's 0. So we start with a 0 qubit, and this was also measured. So we measured it 1,000 times because we looped through it 1,000 times. And when we used 1 as our starting point, we measured it 1,000 times. Okay, so this maybe looks not very surprisingly because it's just just a measurement. But when you think about it, it's actually very interesting that we can now run real quantum computers, now real algorithms on this Q-sharp, with this Q-sharp language, and can actually run our algorithms there. And unfortunately, the time is over for this talk, so I can't actually show you now how Grover's algorithm would work because there's a lot of work to do, a lot of pre-work to do. But I can encourage you, please take a look at this Quantum Development Toolkit at Q-sharp. Give it a try, and I think it's very interesting, a new topic, very interesting new language you have here, and you can play around for it for free. And other than that, thank you very much for joining me on the first interesting path of quantum computing, and thank you.